Hello folks, this is Tom from anti-proton.com, and this is the Spectrum Techniques Universal Computer Spectrometer Model 30, the UCS30. For a long time I looked at one of these and I considered getting one, but I couldn't find any videos of them on the internet discussing anything about them or showing them, and so I was hesitant, and that actually delayed me getting one for quite some time. So I'm putting this video out there so anyone who's interested in them can see them and decide whether they like them themselves. So maybe that'll be of some use to somebody. This is the basic unit right here, and this is the detector and detector apparatus that goes along with it. Technically this is bought separately, but you can get this as a set. So you can buy this, or both together as a set. And obviously you need this, so I'd recommend the set. This device is actually capable of working with mostly any sort of detector, so you don't actually have to get this one, but I actually recommend this one. It's really, really nice. But anyway, let me go into some of the features and details about it quickly. I won't go too deep into it because this is not supposed to be an advanced video. This is supposed to be a somewhat introductory video. This device is a multi-channel spectrum analyzer and high voltage source. The high voltage source means it produces the power required to run a detector like this, which is very, very little in amperage, but very, very high on voltage. You're looking at voltages of 600 volts to maybe 1,000 volts, somewhere in there being pretty normal. Although this thing can go much higher than that in voltage. That's what the high voltage source is. The multi-channel spectrum analyzing part, which is the main job of this guy, is that when signals come back from the detector, this thing is capable of breaking them out by voltage range, how high the voltage is that comes back from the signal, and putting it into little discrete channels. And so as a result, it creates a spectrum based on the power, and the power is based on the energy this is detecting from a radioactive source or whatnot. And so you end up with effectively a spectrum of the radioactive material. That's what a multi-channel spectrum analyzer does. That's what this unit is. Now let's go over some of the basics of what's on the front of it, and then we'll talk about what's in the back. Right off the bat, you have your power. Obviously, it's a little switch for your power. You have a voltage indicator, positive or negative. Mine only does positive. You can get them to do negative, and I don't know if they can do both, but I don't doubt that they could, although I'm not actually sure of that off the top of my head. These two lights in the front here only cut on when you're using it. Acquire means that it's actually sampling the detector, and this will just turn solid. And then you'll get a blinky light here, activity, and it blinks once per signal detected. And of course, for many signals that are really, really high in activity, or intensity at least, this will just become solid. So let's look at the back of the detector. So this is the back of the unit. If you lift it up, you can see it actually has little feet underneath it to hold it into place so it won't slip. Okay, here's the back of the unit. There's a lot going on back here too. Let's see here. You have your power, and that's standard United States power plug on it. So if you're living in Sweden or Finland or someplace like that, and you've got one of those big old weird power outlets, sorry about that. I don't know if they have conversion devices for that or not, but here in the States this works great. You can attach a preamp if you like. Now they have a USB cable, and let me tell you something. Some science devices, I don't know if you've ever bought science devices before, but they tend to use older technology for a couple of reasons. One of the main reasons they use older technology is because it's usually pretty tried, true, and tested. But the problem is some of the old connectors they give you will not hook into a modern day laptop. I don't know about you, but I use this thing constantly with laptop. This USB connection here is a dream. Always use a USB connection. It's very easy. And it's pretty easy to program for too if you write software. Now, they separate positive and negative voltages. Notice mine's only positive. I don't have a connector for negative voltage. These are miniature high voltage connectors. You could probably connect a BNC cable to one of these if you had a converter, but MHV is actually designed for higher voltage, so you probably should be using that. If you had a negative connected to here, then you would see the difference between the two because they would be literally different connectors. Why is that beneficial? Well, it's harder to screw stuff up when you have two different connectors, and I think that's a really good design feature. All right, then you have the input over here. So power goes out to the detector here, and every pulse that's detected comes back to the input here where it's measured, and it goes to the multi-channel spectrum analyzer. These little guys here are kind of interesting. I never actually use any of these, but they're very useful. MSB output is for Mossbauer spectroscopy, something this is actually capable of doing, which is really, really neat stuff. If you select a certain ROI, a region of interest, you can actually configure the device to send a pulse out of this little gate every single time it gets a signal in that particular region. Again, that can be very useful, especially in a lab. You have a gate in. This is for coincidence checking, which would be useful also if you're into looking at more cosmic events or anything like that. And actually, there's a lot of basic nuclear physics experiments that require coincidence or anti-coincidence. And you can have multi-channel scaling devices hooked into it as well, although this device is capable of doing multi-channel scaling without using this whatsoever. And then the temperature compensation cable here connects into a base. If you have a base that connects to this that actually knows temperature, the idea is that you could use this thing to calibrate for temperature on the fly. And that's important because temperature is very important to crystal detectors like this. As temperature changes, the channel in which a particular response is put, a particular pulse is put, changes as well. But regardless, I don't have that feature onto this one, so I have to be somewhat careful about temperature. Now, let's plug the back of this up, and then we're going to kind of go forward. Here are all the cables that go into it. Now, I'll tell you a little bit more about its design abilities and specifications when I'm done with that. I've got a tangle of cables here, don't I? I thought I had this all together so I could pull it right out. Be careful with cables, let me tell you. I usually plug power in last. I'm going to plug it into the detector here first, which that doesn't really matter about order of operations per se, but I usually plug it in last to the actual ground outlet. Now, here's the USB cable. We'll plug that into a laptop in a few minutes. You can see we have this particular type of USB connector on it, as you can see. And then, of course, the standard type for the computer. Give autofocus a minute to get its mind back in order, since I just put something right in its face. Yeah, my autofocus is pretty easy to mess with. All right. In fact, you know what? For safety's sake of my detector, I'm going to move all of these cables away and just spread them out over here, my hands away from the detector. Now, you have high voltage for the detector, which is miniature high voltage cable. It looks like a BNC cable. It's a little different. Let me put that up close so you can see it. Look at that. It looks just like a BNC cable, doesn't it? But it's not. It's a miniature high voltage connector. And on the detector, there's actually a little sign here that says, let me put this to where you can see it, high voltage positive and signal. High voltage positive is sort of obviously where this goes. Let's put that in there. And I'm going to talk about this detector in just a minute. Put that down. Reach down here and get the other cable. This is the signal cable. The signal cable fits into the signal part. So, high voltage, signal. Okay, no problem there. Now, I'm going to put this detector down here. When I was messing around with this earlier, I noticed that moving the cables around was wobbling the detector. So I'm just going to kind of jam this up together because I only have two hands and I'm trying to do a camera. So this way this doesn't roll around while I'm maneuvering the... See, it's already moving it right there a little bit while I'm moving these cables around. Okay, now, I suggest putting in the input first because you always want your input and you want your power to be connected at the same time, right? You don't want to have power going in and nothing coming out. That would be very bad. So if you put your input on, and if you were to find out that this unit were somehow hot, which it isn't, but if it were, then it would be less damaging. So let's put that into positive voltage. Make sure these fit snugly. You can hear them snap when you put them on there. Now, we are ready to rock and roll. But first, let's talk about this detector just a little bit, and then we can talk about the MCA just a little bit too. And then we're going to hook this thing up and use it. This is a sodium iodide thallium dope detector. That means it has a sodium iodide crystal right here in the head. That sodium iodide crystal is, in this case, 38.1 millimeters long. It's 1.5 inches, okay? And it's otherwise a cylinder shape, so it's about the same shape as this. This has an incredibly thin layer of aluminum over the front of it. I mean, if you could poke right through that pretty easily. And the reason for this is that the aluminum blocks really, really low energy X-rays, and you want to be able to see the X-rays, so they make the thinnest possible aluminum they can get away with. This device has a 10-stage photomultiplier tube that takes the flashes of light from the crystal, the photoelectric material here that produces electrons when it's hit by those little pulses of light, and it amplifies those electrons as they go down the tube, 10 stages of it in fact. creating a little pulse here in the end every single time it detects something, and the voltage of the pulse is proportionate to the energy that detected it. That's how it reads energy in the first place. This is a radiation sensors device. The model is 6S6P 1.5 VDC2. It's got a crazy model number. But anyway, it's rated at 625 volts positive to 800 volts positive, and it can go all the way up to 1,000. But after you go over 800, you're starting to eat a little bit into the life of the unit. So I wouldn't recommend constantly going over that amount if I could avoid it. Let's hook this whole thing up, and we're going to fire it up and do some basic gamma spectroscopy with a couple sources to show you how it works and how to configure it and everything too. Before I go any further, point out the basic details of this guy in case you're curious. I'm just give you some quick technical specs. So if you're not into technical specs, just give me a second. This will be over with. The number of channels that it divides the signal into, the more it gives you, the better, the nicer and smoother, of course, everything looks. But of course, in some ways, you can argue that having fewer channels makes it a little bit easier to read the actual spectrum. But regardless, this unit can take 1,024 channels. That's how many it has. And you can tell it to show less channels. You can drop it down to, I think, 256. But it does actually have 1,024 channels in it. You can buy these guys all the way up to 4,096. You notice these are powers of 2. But anyhow, I didn't get that. I got the 1024 because that's all I need for this detector right here, and I don't have any other type of detector to connect into this. This guy has a pretty fast clock. It's 80 megahertz. It's capable of taking pulses in the 1 microsecond range, so you can get a pretty hot source in front of this thing and not really miss too much. It has a dead time timer built into it and compensator, so it's able to figure out how much of its time it's not able to be recording because it's in the middle of, grabbing pulses and so on, and it can account for that and adjust your runtime to actually take into account that. It has a 3-channel range, a 3-byte range for channel information, so it can hold a pretty large. I'm trying to think how many. I think it's 16 million. I think is the maximum number of accounts per channel it can have. But I'll look at that in just a minute and let you know the exact number. And that should be pretty much all you need to know for that. Now let's fire this up and look at the actual software and get an idea what's going on. All right, folks, let's work with some radioactive materials. First off, always have a Geiger counter when you're working with radioactive materials. It's a good idea to have a Geiger counter. Why? Because then you know what's going on. It's a smart thing to do. It's just, a nice little detector to have. Now, the materials I'm working with are really low in activity. They're reasonably safe to work with. So this is probably not needed, but I have it here just because. The detector's ready to go. It's primed. Just need to fire up the power. If you're working in a lab, you'll probably have something a little bit more hardcore than just a Geiger counter. You'll probably have a dosimeter. And just for fun, here is the Polymaster gamma spectroscopic dosimeter. I'll put this on top of the MCA. Ironically, this is both the detector and an MCA as well, so it's kind of ironic to have it here. And it's detecting the actual material. As you can see, it's going bananas. But anyway, we're going to set this thing to calibrate mode so that it will shut up while we're doing the test. Now, if you open up these little metal things here, these actually come from Spectrum Techniques also. You can buy these. They don't come with a sticker though. Sorry friends, you have to get that yourself. If you open them up, you can find between 1 or 2 disk sources in each one of them. And let me put the source up close to the camera so I can see them. This is a cesium-137 source. Let's see if the autofocus will work. Autofocus. There it goes. And this guy right here is a 1/10 of a microcurie, which in the term of becquerels is 3.7 kilobecquerels. So approximately 37,000 disintegrations per second occur inside of this. This is cesium-137. Chernobyl, Fukushima, that sort of thing. That same sort of material. All right. We have some more of them in here we'll test in a few minutes too. Now, let's fire everything up and we're going to test this. The original plastic tray that came with mine, I don't have it anymore. I wore it out. Like I said, I put about 1,000 hours of usage out of this device already, so I've really logged a lot on it. And I use this aluminum one right here. Plastic is probably better than aluminum because the aluminum will cause something called X-ray emissions that come off of it. Well, you get brimstone, you'll also get X-ray emissions. But regardless of that, I filter those out. Well, not in this example, but normally I do. And I also don't normally use the little tray right here. So we're going to start this thing out with a cesium-137 source. Wait a minute. Let's take a more powerful cesium-137 source. I like my little one, but let's go with a more powerful one, okay? Let's go for broke. This is a lead pig. Geiger counter is already responding. Let's see. Cesium-137, cesium-137. Here we go. Cesium-137. This is 10 times more potent. Autofocus. This is a 37 kilobecquerel. That's 37,000 disintegrations per second, or if you like, 1 microcurie source. Put that over here. Now, let's take this, and we're going to put it on the detector. I like putting it emissions face up. And we're going to stick it down here a little ways. Not right on the detector, but a little ways away from it. Okay? Let's fire up the detector. And the power cut's on. Now, everything else we're going to do is going to be on the computer, so let's switch over to the computer's view of everything. Alright, this is the software that comes with the actual device itself. And as you can see, I have the actual version information out here to look at. Let's close this. And it's a pretty straightforward piece of software. Right across the top here, you have some easy access buttons. This stuff can also be done through the various file type menus that are up here at the top. And of course, there are some more easy little buttons down here at the bottom. Now, let us uncalibrate this unit because we don't know what the calibration is yet. And you notice at the bottom here we have 0, 256, 512, 768, and 1024. These are the channels. Channels, see the channels? And there's nothing in the channels because see, here's the channel number we're in. And here are the counts that have been found in that particular channel. You notice there aren't any. This is where the energy would be listed if the energy were set right now, which it is not. You can set regions of interest down here. So you type in the beginning channel and the end channel and click set or clear them. And there's other ways to do it as well, I might add. You have start accumulation, stop accumulation, and clear the spectrum. You have some voltage settings, timer settings, integral settings, peak report, data report, region of interest, linear or logarithmic view, everything you need right there, but you can also access this stuff in the menus here. You have your high voltage power set to 650 volts right this moment. It's off. We'll cut it to on in just a minute. You have your gain, your coarse gain and your fine gain. This spreads the energy out across the channels and adjusts where the channel energy lies in the channel itself. Okay, let's fire up the voltage. And before we do that, let's go and look up first off the mode we're in, which is internal preamp, which is what we're using. And this is a pulse height analysis. There's actually several other modes you can do. You can have an external amp. You can have direct. I don't believe that uses an amp at all. You can perform multi-channel scaling, internal or external power, and internal or external scalar. Basically, what that does is it counts the number of counts from all energy in a particular channel for a particular period of time, then it moves to the next one. And that's really good for decay analysis. If you had, let's say, radioactive rain and you wanted to know why it was radioactive, well, this right up here would tell you the isotopes involved. This down here would tell you the rate of decay. And of course, Mossbauer spectroscopy can be performed, which is quite an interesting form of gamma spectroscopy that involves bombarding iron with gamma rays and so on. It's actually quite complicated. It would be a video unto itself, but we're not going to worry about that today. We can look at peak reports, set calibrations, create display lines for common isotopes or add our own if we want to, zoom in, zoom out, colors. Here are the settings, like the voltage settings and everything. We'll get into that in a minute. We can load backgrounds, clear backgrounds, do all kinds of neat things. So let's go here and let's go to the voltage settings and make sure that we're set at 650 volts. Yes. Correct polarity. Right number of channels. There are discriminators. We can tell the unit we don't want to look above or below a particular amount of energy or voltage or channels or however we have this configured. In this case, it's in channels, and low is set to 14 and high is set to 1024. We have coarse gain and fine gain, which, as I said, determines how this spreads out, and we're going to set this and leave it the way it is right now. This is correct. And so we'll cut the voltage on. We can do it right there, or we can just click the voltage on button here. Voltage is now on. All right, let's click accumulate and see what we get. As you can see, a spectrum immediately forms. Anybody who's familiar with gamma spectroscopy will instantaneously know exactly what isotope this is. It's sort of cliche. If you're not, then I'll inform you. This is a cesium-137 isotope, and you're looking at the barium-137M gammas that come from it. And if you don't know what I'm talking about, simply to say this is the isotope cesium-137. This is a logarithmic view. So as the counts go up here, they go on a logarithmic scale. You have 16 counts, 256, 4,000, 64,000, 1 million, 16 million. For example, this high point right here, if we select this particular channel, let's get that channel exactly. Channel 34 is experiencing, see, 360 counts, 370 counts. It's going up pretty quickly. So let's switch to a linear view. In a linear view, we've already overwritten the entire view screen from 0, 8, 16, 24, going up in a linear fashion. So let's adjust the slider here on the side to pull these down. This is changing the counts here, the space in between the counts. Let's drop that down. And as you can see, this is a little bit easier to see. You can actually pick out some of the actual parts of the spectrum. Here's the primary photo peak from cesium-137. This is the Compton Valley. That's a Compton peak. This is a backscatter peak. This guy right here would be the lead donut that's around the actual detector. This X-ray emissions from that. And this is the K-alpha 1 and K-alpha 2 X-rays from the cesium-137. Neat. All right. Using this cesium-137, we can perform an actual calibration. Now, we can do this manually, knowing the channel and knowing the energy, because we know what the spectrum for cesium-137 looks like. And knowing this guy right here, we could just go to Settings, Energy Calibration, and we could do a 2 or 3 point calibration. Let's do a 2-point calibration quickly. The unit that we're going to use is thousands of electron volts, keV. And we're going to select this channel right here. Oops. There it is, channel 34. And we're going to say that that's 32 kiloelectron volts, which we know it to be because we've studied this isotope before. This guy over here is about channel 725, and we're going to say that it's 662 keV, which is pretty close. The smarter way to do this would be to take a region of interest, and let's select an area here and do that. There's a region of interest. Like I said, oops, we're in the middle of an analysis. Let's stop the analysis and do it. Oops, didn't take. There, that's better. If you do it this way, then if you hold your mouse over here, you can see what the actual centroid is. We've already calibrated the unit, so let's cut the calibration off for a second. And you see the centroid is actually at 724, and I don't think 724 is the actual channel that we chose. No, we didn't use 724. And so this is a slightly better way to do it. And I'm not going to go into the details of how to perform gamma spectroscopy because that's not really the point of this video. And you guys may already know I have videos out that explain how to do this. I'm just kind of giving you an overview of the features. You can do the same thing for this energy over here as well. And I'd like to point out that we're getting pretty good resolution on this thing. Look at the resolution. Not bad at all. All right, now let's use the auto calibration feature, because we can do that too. Auto calibration requires a cesium-137 source of at least 37 kilobecquerels. I can do it with a 3.7, but it doesn't work very well. It's better with a stronger source. We select auto calibrate, and we sit back and relax. As you can see, we've finished, and the device has set itself for 650 volts, coarse gain of 2, fine gain of 1.94. It has also calibrated everything down here. Let's see if that's correct. We'll clear the spectrum, start it going, and obviously we're in logarithmic view. I'm sorry, we're in linear view. Let's change this down a little bit here so we can see. And we're getting almost right on the dot. Look at that. Pretty good. We can put a peak finder on this unit. Go down to peak finder, and peaks will show up automatically. Not bad. So we're pretty dead on for cesium-137. I'm sure at this point we can now test a few more isotopes and see what else we can get. So let's stop the spectrum. And I'm going to replace a different isotope. This time, let's try a little more higher energy isotope and see if we can identify what it is. Okay, now we have a little bit more powerful isotope in here. And you'll notice that I've changed the calibration. I just went ahead and calibrated it because, like I said, this is not a video to show you how to do this. This is just kind of showing you off the actual detector itself. And now I'm looking at a range of 8 kiloelectron volts to 497 to 1024 to 1589, all the way up to 2192 keV. And this unit can go higher than that, but usually I try to work in this first range down here. All right, let's cut the detector on and see. And I have the isotope match kind of ready to go in just a second, and then the auto peak detection is running. And as you can see, there's two peaks that are really forming out of all of this. There's a peak right here at 1173, 1175, somewhere in that range, and there's a peak right here at 1328. Let me stop this for a minute, clear the regions of interest, and we're going to select just this region of interest right here and this one right here. These are the two photo peaks. Let's get that going again. Let it keep going. By the way, you can set the UCS30 to do timed counts. You can set it to do batch counts, so it does one and then does another and so on. It can be set to do all of these things. You can set this thing for at least 24 hours of runtime continuously. I know I've done it before. And by the way, live time is the actual time that the detector is open and able to actually take samples, versus real time, which is how long the detector is running. And this is the dead time meter. It's showing you what percentage of the time the meter is not able to read anything because it's in the middle of reading other stuff. The higher the source rate, the sample rate, the greater that number can be. Let's switch to a logarithmic view. And there you go. Okay, so stop this. Let's get rid of the peak finder. And let's see if we can find an isotope that matches this. I think I know exactly which isotope it is. If we tried cesium-137, you would see there's nothing there. Europium-152 is all over the place. Let's try cobalt-60. Well, how about that? That's a pretty good match, wouldn't you agree? And this is cobalt-60. It's about 33 kilobecquerels worth of it. All right, let's cut that off for a second, and we'll clear the spectrum. Let me stick on one more isotope. Well, we'll give it two more, and just to give you an idea, just two more. Here's an isotope that's kind of interesting. This one's actually a very interesting isotope, to tell you the truth. Let's run this and see. Let's get the peak finder back on. See what we see. Look at that guy. What could that be? Well, let's stop this for a second and clear the regions of interest. Get it going again. And right off the bat, you see that this is approximately at 511 kiloelectron volts, pretty close. And that over there is nearly 1274. So this is sodium-22. Sodium-22. And again, I'm not going to go into the details of isotope detection. That's another video. Let's see if we have sodium-22 in our isotope match. Na22. Yeah, they're there. Definitely. All right. One more. Just one more. Now this is an interesting one. I guess I said the other one was interesting too, but this one's really, really interesting. It has a lot of energies. This one's sort of infamous. Let's see if you know what this one is. If we switch to a linear view, whoa, you can see these low energy X-rays over here are just filling up like crazy. Let's go back to logarithmic. This is Europium-152. Europium's pretty active too. You notice the dead time meter is going nuts, and you notice that this thing is actually processed already less than 1 second less than this, almost 2 now. And we can compensate for that if we were to do a long-term analysis. We can actually set this thing for 3,600 minutes or set it to 3,600 seconds, or set it to like an hour or a day or whatever we want. You can also load a background spectrum, and you can clear a background spectrum from this to actually clean up the background. Oops, let's stop this. For example, if this peak right here were always in your background, it would show up in a spectrum you're doing. You could load a background and you could remove it. So that would be useful. You can also smooth the spectrum too, which is also very useful. Now we can do multi-channel scaling mode. Let's do that, multi-channel scaling. And now each one of these peaks will fill up with as many counts as it can take for whatever this dwell time is. Let's set dwell time to something lower than 600 seconds, which is its maximum. We're going to set it to 4 seconds. Now, this is going to fill up here, and let's change the display just a little bit so that you can see pixel size to 3, a little bigger. And let's start it. I don't know if you can see that or not. Let's zoom in. Okay, we're zoomed in. Now, if you see zoomed in, this is filling up pretty quickly. And if you were to take the maximum range here, in this case 18,933 counts, 19,000 counts, whatever, divided by the seconds, in this case 4 seconds, you know how many counts per second you are getting. Now watch what happens when I move the source away from the actual detector by double the distance. Alright, now it's double the distance away. Let's see what it does. See? It drops. And as a result of doing this, you can actually do decay analysis too, which is very useful. You could set this for a much longer period of time and make a nice decay curvature from something like rain. Alright, so we can take out the sample, put it away, and we're done testing. So the UCS30 is quite an amazing device, and this probe right here is pretty good too. Some things to consider: if you're getting a unit, you might consider a bigger probe if you can. If money allows, I would get a 2-inch, even a 3-inch probe. Nothing smaller than a 1-inch if you can. These guys aren't particularly cheap, of course, so that all boils down to how much money you can spend on them. If you get one of these units, you pretty much nearly have to get at least a cesium-137 check source. I would recommend a 37 kilobecquerel, that's 1 microcurie, if not more. The actual combo unit that they sell comes with a collection of these little sample discs. Let's see what we have here. We have Europium 152, cobalt 60, and sodium 22, as well as cesium 137. And underneath here I have another cesium 137. These little discs are about $50 a piece, something to that effect, plus or minus. To get them assayed like this one, and this one are, is another at least $100 on top of that. And that's really only useful if you're going to do a activity analysis. I actually do activity analysis, so I actually need that. And it's a good idea, I believe, to get a lead pig like this guy to stick them in. I'm sorry that these neat little radiation symbols don't come with the actual unit. I paid extra for those and bought them off the internet. They're very useful as far as I'm concerned. Obviously the Geiger counter and dosimeter don't come with the unit either. These are things from my lab. But anyhow, I consider it to be a very good instrument. The pros and cons are as follows. The pros: this thing can run by itself without being connected to the computer. It does need to be connected to the computer to get data off of it or anything like that, but you can unplug the computer and leave it by itself for many hours if you want. I like the fact that everything's contained inside of it. It's nice being a hardware device over software. Software can crash and cause problems. Being a hardware device makes it pretty stable. I like the fact there's a lot of functionality in the back, things I can do with it later on if I want to. I can connect a lot of other probes to it. It's really, really just a nice device. Cons, things against it. Well, it's expensive, but then again, I guess you get what you pay for too. Don't get me wrong. I mean, like this little guy right here wasn't cheap either. So it's a little expensive. I would prefer if the temperature control device that was built into it functioned correctly with this probe. This probe doesn't have a base that connects to it, and the software component of that doesn't exist yet. They haven't put it in. So that would be something very useful, because I find temperature calibration to be something that is quite important with sodium iodide probes, or even cesium iodide probes like this guy right here. Other than that, I'm pretty satisfied with it. I don't really see any particular problems with it. It actually runs really, really well. It had trouble with one of my computers, but I think I've traced that to actually being the computer that has the problem, because all my other computers this thing runs great with. I've never had otherwise a moment's problem with it. And I've logged at least 1,000 hours of usage out of it. And as you can see, it's running right now, picking up background. And it's very sensitive. I find that it's sensitive enough that I can actually do analysis of cesium-137 contamination in soil. I find that I can detect the potassium in a single banana. That's pretty good. That's actually really, really, really good. So this is my primary device. In the field, I carry this guy, and I carry my Gamma Spectacular GS 1100. But back in the lab, I use this unit, because this is basically a laboratory grade unit. This is not for carrying around with you. You put this in the lab, and that's what I use in the lab. That's my primary unit in the lab. So this has been Tom from anti-proton.com. If you have any questions about the unit or anything like that, let me know, and I'll be happy to answer them if I can. There you go.